Okay, curves of intersection. So I'm gonna do a super quick recap before we jump into that. So we talked about space curves. C given by a vector function, which now we saw inputted of a scalar t, and it outputted a three-dimensional vector that was drawing your space curve. Okay? Oops. Is that what we were calling g of t? D of t and h of t. Okay? And so what we want to do in this part is we want to figure out, we practice graphing cylinders, we practice graphing like cones and all this stuff called quadratic surfaces, which was pretty tough. So what we're going to do now is there's two surfaces that intersect each other, and they intersect at some kind of curve. And so we want to find the vector function of that curve where they intersect. That's kind of the goal. Okay? Let me write that. So goal. So find the vector function of a curve of intersection between two surfaces. Luckily, it turns out we don't even have to draw anything, okay, to answer it. But I will show you some visuals to kind of solidify what's going on. And so let's take a look with an example. So you'll see something like this on the homework. It'll say find a vector function for the curve of intersection between the surfaces, and I'm gonna give you the equation. So one of them has the equation x squared plus y squared is equal to 4, and then the other one is z equals xy. If you draw this on the xy plane, what did that look like? Yeah. Circle of radius 2. Which variable is missing though in 3D? So it's a circle of radius 2, but since z is missing, what's happening? It's a circle that just moves up and down in the z direction, so it's a cylinder, right? So this is a cylinder, and this is some other funky surface, okay? And it's gonna intersect that cylinder, and wherever it intersects it, or it has a curve, that's our job, to learn how to parameterize it. What does that mean? I need to find a way to write the x coordinate in terms of a function of one variable. And therefore, if I can find x in terms of a function of one variable, then I want to be able to find y and z as a function of that same variable as well. If I can do that, I can write all three of these coordinates in terms of one variable, then I can let that variable I can let that variable act as my t. Okay? So in these problems, if there's a circle involved, you're going to want to use your knowledge of polar coordinates. Okay? So we know that on the xy plane, this represents, let me write this a little bit here. This represents a circle of radius 2. Circle of radius 2. So how can I use polar coordinates to to tell me how to write x and y. Okay, remember? Jacob?
X is parameterized by 2 cosine t, and y is parameterized by 2 sine t.
2 sine t. Yeah. R cosine the angle, right? R cosine the angle. You could use theta as well if you want to in polar, okay? But just because right now we're using the variable t, I think in this section that your textbook will just switch the theta to a t. Is that cool? Okay. What's tricky about this is that there's no real algebra you do to get this. Like this, you purely have to know from your knowledge of Calc 2. Okay. So I know that in Calc 2, a circle of radius 2 can be parameterized by 2 cosine t and 2 sine t. So what do you think we can do now? See how both of these two variables are in terms of functions of t? Now what's our goal? To get z in terms of t. So what can we do here?
Multiply.
Yeah, just plug in the x here with the function that we set it equal, right? So from here, we can set x to be this function that we set it to be, 2 cosine t, and y can be the other function, which is 2 sine t. So then that tells me that z is 4 sine t cosine t. Use your trig identities. Is there a way to rewrite that? Yeah. If you look at this as 2 times 2 sine t cosine t, what is that right there? Sine 2t from trig identities. So I can rewrite this as 2, and this is sine 2t. Okay. Go back to those down. So now my goal was to parameterize all 3 coordinates in terms of one variable through some different functions, and I was able to do that. Okay, x is in terms of a cosine function, y sine function, and I was able to write z as a different function, but all of them use the same variable t. Okay?
Why don't we try another way? So I can say x equals t. So we can solve for y based on t, and then we can plug in z.
Totally. That's where I was. Yep. That's where I was going.
I mean, let x equals t.
Yep. So there can be multiple answers. That's what ends up happening. It all depends on the functions that you start with to build that. So in this, we use these 2 functions to build this vector function, right? So one of my answers could be this. This is 2 cosine t, 2 sine t, and z is 2 sine 2t. That's a possible parameterization or vector function that would parameterize my curve. Young here, you're noticing that there's a different way you can do it. You said, what did you say?
I said x equals t.
Okay, so let's see, you said let's let x equal t, and then if we do that, we can
So for y.
Yeah, replace this x here with a t. So notice that the x squared plus y squared is equal to 4. I can now rewrite that in terms of t. There's going to be a little hiccup with this, okay? So here, you isolate the y squared. And then what do you have to do?
You take square root of 4 minus t squared.
When you apply the square root to an equation, you have to consider the plus or minus. So now you actually end up with two things. You end up with plus or minus square root of 4 minus t. But it has to be a function, so you can't have both of them. Okay? And then what can you do with this and this?
So you plug in c.
We do similar thing. Plug the x here with the y that you got, but you can only, you're going to get 2 possible z's, one with the plus square root, one with the negative square root. Okay? So
We can take either.
we're going to see that if I do the plus one, what kind of y coordinates, what would be the sign of the y coordinates?
Positive.
It'd be positive or 0, right? But they can't be negative. You wouldn't have any negative y coordinates. But if I do the negative one, you wouldn't get any positive y coordinates. So the issue is that you won't be able to parameterize the entire curve. You're only going to parameterize parts of the curve depending on the one that you choose. So in this case, it didn't work out to parameterize the whole thing. Okay, we'll look at that in GeoGebra. So let's see, if I plugged in, we got x times y. X here we're calling the t, and y you're going to get plus or minus 4 minus t squared.
So can t be positive? Can t be negative?
T could be negative. Yep. So then you end up with plus or minus t 4 minus t squared for z. So you technically end up with 2 vector functions. You're going to end up with x being t, and then you have to choose the positive or the negative. Okay. Let's say I chose a positive. So then z will be the positive as well. Or I would have to choose the negative. And then this would be the negative as well. So that's the only issue there. And we'll look at it in a little bit. But there will be times though that for example, if both of these were squared, right? Then the y squared, if these were both squared, then you don't have to square root. I mean, when you plug this in here, it'll square it, and then the plus or minus will disappear, except that you might end up with a plus or minus still here. That's the only thing that's making this a little buggy, but we'll see. Someone had a question. Yeah. No.
So we set it up as like 2 vectors for one function, and then like set the domains for 2.
Kind of like use both of them at the same time somehow? Ooh. I think if we were to do something like that, you would have to do a piecewise function.
Yeah.
Yeah, you would have to do a vector piecewise function. Cool. Where basically it would be the positive one here. And then the bottom one here. Whoa, I've never even seen that. That's cool. I've never seen a piecewise vector function. And then you would just specify, right? Like you would say this could be if t, ooh. Yeah, if t is positive, hold on. Because the thing is that this domain of this, the domain of these two are the same. It's the outputs that are different.
So it's not possible.
Let me see, let me think about it. Like, let's say you said time was 1 or time was negative 1, right? If time was positive 1, at t equals 1 and at t equals negative 1, you would get the same. Oh, no, you wouldn't, because this would be different. No, let's say the outputs would be different. I think you would still miss stuff, because if I do something like this, for example, right? If I do something like this, maybe not, let's see. These, oh wait, no, yeah, that'd be different. Because here, if t is negative, like let's say negative 2, this would be negative, this would stay positive, and this would be negative. But if you have a positive 2, positive, 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 so then here, if t was negative 2, this would be negative. Yeah, see, it wouldn't, like, if I called this R1 and I call this R2, R1 of -2 is not the same thing as R2 of 2. Because here, if I plug in a -2, this would be negative, positive, negative, the outputs, right? But here, if I plugged in a +2, it would be positive, negative, positive, which wouldn't agree. And if I plugged in a -2, it'd be negative, 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 positive. It still wouldn't agree. Yeah. Let's take a look at GeoGebra. Let's see what's up. Chill. Okay. So let's take a look. Can you guys see? All right. So let's see. This is a different problem. Whoops. Okay. So we got, it was x squared plus y squared is equal to 4. 4. Okay. So there's the cylinder that we guessed. And then we got z equals xy. Let's have them be different though. Let's change their color to something like that. Okay, so they seem to intersect at a Pringle. You know the Pringle chips? Looks like a Pringle chip, right? Can you guys see that? Oh shit, you can't. Can you guys kind of see it now? Right here? Let me make it a little bit lighter. Color, let me make it a little bit. Okay, is that better? Okay, you guys see the Pringles chip kind of? Okay, now let's see. So let's do the first parameterization we did, which was I have to put curve, then my 3 functions, I think what were they? 2 cosine t, 2 sine t, 2t, right? And then I gotta tell GeoGebra, t is my parameter, have it go from -10 to +10. And then there's my curve that we parameterize. If I delete everything, it just now, all I have is the curve, the space curve, okay? Okay, now let's try the other one that we got. So let's do R1. So that's gonna be t. And then what was the square root of 4 minus t squared? Oops. And then was it t? And then the same thing? Okay. 4 minus t squared. And then it's t. Let's say I do all, oh wait, hold on. What's my domain here? Because now I have a square root. We want this to be positive, or not negative, right? Oh, okay. What does the graph of this look like? And if I put it like this in the xy plane, upside down parabola shifted 4 units up, where the intercepts are going to be -2 and +2. Right? When is the parabola positive or 0? In what interval is the parabola on top? -2 to 2, right? So that means that the domain of all this vector function is restricted. It only goes from -2 to 2. Otherwise, the stuff inside the square root will be negative. So in this case, I need to go from -2 to 2. And let's see if that parameterizes all of it. So it's only going to parameterize, as we said, where the y coordinate will be positive. So it's only part of the curve where y is positive. Okay. If I go from 0 to 2, kind of like what we were trying to do with the piecewise function, that's only going to do this part. Okay. Okay. Now let's do the same thing. Curve t. Here, can I just duplicate this thing? Okay, but let me do, there was a negative here, and there was a negative here. So now that gave me my other part. Let's color that pink. Like that. So the pink one, R2, which we're calling R2, that only gives you y values that are negative, which is what we were saying, right? If I try to do a piecewise function where this goes from 0 to +2, and this goes from -2 to 0, and then 0 to 2, see, it's not going to give me the whole thing as I wanted. I need them each to have the domain. So the summary is, these give you parts of the curve, but it's only this one that gives you the entire curve that we want. Okay? That only happened because of that square rooting step. It gave us a plus or minus. Okay? Sweet. Any questions, guys? Okay, so I'm gonna have you guys try one. Practice it out. Oh, yeah, no, okay. All right, guys, so practice this out. So find a vector. Yeah, I guess it's just say find a vector function. Yeah, not the vector function. Find a vector function for the curve of intersection. Curve of intersection. Okay, and so I have two. I just want you to finish the first, but if you finish early, you can do the second one. So the first one uses these two curves. Sorry, surfaces. This bad boy here. And the second one, if you have end up finishing early, uses these ones. I don't care which method you use, just make sure that if you run into a step like this, that you know you're not going to answer the full question, because they won't parameterize the whole curve. All right? So you guys can just check over each other. And then you guys can clump up there and check in everything. Remember, this we were able to do polar coordinates because on the XY plane, it was a circle, radius 2. It was on the XY plane, okay? It could be possible for another plane for that to happen.
Oh, and then you
You're not wearing your famous Zelda hat, man. I was trying to match with you today. You lost it? Sorry to hear that. Yeah, yeah.
Cosine squared t minus cosine squared t.
In that case, it's
What? What if you sine 4 of 0 cosine squared t minus cosine squared t? Oh, it's cosine.
yeah, because there's not a square. Yeah, cosine 2. Cosine 2.
That was the XY plane. I'm not sure if it's the same thing for as Y. So it could just be
Would you that's the cosine I think so.
I think it's way back to like and then we have to know what y equals.
Minus sine squared equals cosine.
That's my assumption.
So we get 1 minus 2 sine squared t equals y squared.
You could do it like that. But here we go.
Oh my god.
Yeah, you do that now.
And I got 4
Correct.
It wasn't if it blew your mind,
If there's circles involved, then yes.
Cosine squared minus sine squared.
If there's a different equation involved, yeah, I mean, yeah, stuff like that, like the second. And then in that one, then you might have to.
I need to look them up better to compare. I have none of them, but like look for the
You guys can check it.
cosine squared plus
Oh, we do that.
If you haven't yet, please check with your classmates. Check your notes. Oh,
That's what. I'm making like a Yoshi right now, but I haven't really done a lot of stuff.
I finished the practice session.
like real life
I don't want to see that one. I guess because I for study guide is what you provided by all the formulas. But he said study guide is actually the condition. I thought I can just look up some formulas in the study guide. I guess you say provided maybe to the extent, but I don't think they would.
Yeah, we were.
I don't know.
I think we were maybe supposed to put like an equal sign, like on like our. Most likely just has to be very close.
You know what I'm supposed to? I took L2.
Oh, good.
I had three. I guess he's famous for his
All right, guys, so here's some possible answers. Most of you guys realize this is polar in the xz plane with radius 1. So you let x be cosine, you let y be sine. Subtract the z squared over here. And then you end up with y is x squared minus z squared. So then you plug in those functions. Cosine squared minus sine squared was a trig identity, which is cosine 2t, which has other identities. It's like 1 minus 2 sine squared t and 2 cosine, like there's a lot of cosine 2t. Any of those that you write are all equivalent, so the answer is right. Okay? Cool?
Back to the first part of that, you can use the z as the sign.
Yes, if you graph this on the xz plane, you can think of z as like the y, and so then that would just be a circle of radius 1. And so with polar coordinates, that would be 1, for x would be 1 cosine t and 1 sine t. Yeah. But it would be on the xz plane. Okay? For this bad boy here, trig that doesn't really work, so you would want to try something like what we did in this problem. Notice that y is already written in terms of a variable, x. So then if you let x be t, and then plug in the t here, then y is t squared. And so now you got two variables in terms of that one variable. So then just plug them in here, and it simplifies to that. Okay? In this case, this is okay because we didn't end up with any square root stuff that gave us restrictions. So you're able to plug in any value and it outputs all possible values. Okay? On the notes, I provided a picture of the two surfaces and the curve of intersection they use parameters. It'll be in the notes. Okay? Sorry.
Just cosine t, whereas this one was
Because of the radius. Yeah, exactly. Yeah, this had like a 25 here. What would be the radius? 5. So then it would be 5 cosine, 5 sine, and so on. Yeah.
So if you had something in the zy plane, would the y plane then be cosine?
Yeah, good question. So if this was a y, then you'd be on the yz plane. So now y is like the x. So you would let y equal which function? Cosine, and z would be sine. Exactly. Yeah. You're going to do that a lot in this section. All right, guys. So that's the end of section 3.1. That's what we weren't able to finish, but it was very important, So I wanted to make sure we covered it. What time is it? Okay, cool. All right, so now we're going to finally do some calculus. Okay, we're going to do some derivatives. You're going to have to review all those integration techniques, trig integrals, maybe trig substitution. I don't think there's partial fractions, and there might be one or two. But yeah, all those come back. I'm sorry. I'm the messenger, don't forget. I'm just the messenger. Okay, let me open up a different section here. Okay, so to get us started, I do have actually no, we gotta jump onto it. So derivatives of vector functions. Let's talk about that first. You guys learned derivatives and their connection to slopes of a tangent line in Calc 1, right? So let's see here what the heck this is going to be. So let's let C be a space curve with vector function R. Some vector function R, okay? And let's kind of put some pictures here because you're going to want some visuals. X, Z. And let's say this is your space curve like this. Going through there. And the orientation, let's say it's this way. So the points are moving this way. Okay, so in 13.1, we learned that you have your vector function, you plug in the t value, and then it corresponds to some point on your curve, like that. Let's call that point P. Okay, and then we're drawing it out. Now, yeah, wait, you guys are still drawing. Let's say this is at time 1 second, okay? If we add time, let's do it at 2 seconds, where will the vector function be? On this side or on this side? If this is the orientation, it's going to be going this way, because the orientation as t increases, it's drawing it in this direction, right? So let's call that future time t plus h. So now, at r of t plus h, which is a little bit more than t, we're over here now. We're at some other point. Let's call that q. In calc, when you guys define the derivative, you guys remember the difference quotient? It was f of t plus h minus, or f of x plus h minus f of x over h. Maybe that sounds familiar. But basically, if we subtract these two, what is the result? A number or a vector? It's a vector, remember? It's a vector. And what does that look like? That's r of t plus h minus r of t, which is backwards, so it'd be like this. And it's going to be this vector right here. But remember, the way the textbook's doing it is they're going to draw it. We do the black. There's no black on the top. It's going to be like this. That same vector is this vector right here. That small vector right there is just placed here. So this is r of t plus h minus r of t. That's the difference vector. Okay? And in calc, you took a limit. What was the limit? What was approaching 0? H was approaching 0. So what's going to happen to this picture if h is getting closer to 0? This vector starts to get closer to this point, right? So it starts kind of going like that. So what happens to this vector? It starts to get smaller and smaller and smaller and smaller, okay? So this is how we're going to define the derivative of a vector function through that kind of process here. So we're going to say for a vector function r of t, its derivative r prime of t is defined as, use similar notation, dr dt, as you did in Calc 1, which in prime notation looks like this. We're going to say this is the limit as h goes to 0 of r of t plus h minus r of t over h. So nothing too different from what you guys learned, but in terms of the things that are being subtracted and being divided, they are very different. Okay. Is the numerator a vector or a scalar? It's a vector. It's this one right here. Is the denominator a vector or a scalar? Scalar, right? So what does it mean to divide a vector by a number? This is really just the vector r of t plus h minus r being multiplied by the scalar 1 over h. So it's just scalar multiplication. Okay? As, and there's a limit in front of it. Okay? As h goes to 0, what's happening to this vector? It's getting smaller, right? Its magnitude is getting smaller. But as h gets smaller, what happens to 1 over h? It's getting bigger. So it's the magnitude of this vector is getting smaller, but this kind of balances it out so that it actually stays pretty big. Okay? So what ends up happening, I run out of colors. This orange sucks, look. I just want to throw it to the wall. Have I guys told you that story? So when I was at Cal, I was taking my last math class, and there was a 16-year-old in that class. And he was like this little prodigy kid that kept correcting the professor. So he would always raise his hand, and he'd always kind of correct the professor what was written on the board was incorrect, and he was always right. And then there was one day where I forgot my glasses. So I sat in front and I asked the professor if he can, there was a big chalk, because they use chalkboards. There was a big thick chalk, and I was like, oh, can you use the big chalk instead of the small chalk, because I don't have my glasses. And that already kind of really made him upset. He said, okay, fine, I'll do it. So he grabbed them. So class was going, and he wrote this like half of the board proof, saying something wasn't possible. And then, of course, the little kid was like, it is possible. Can I show you the example? And so he goes up and he erases the professor's work. And then he showed an example, all this fancy algebra that it was true, and it was fucking true. And then we all just started clapping. And then the professor grabs the chalk and throws it to the wall. And we get super pissed, starts cursing and stuff. And we were all like really scared. And then he just kind of calmed down. Like, sorry guys, that was funny, right? No, that was fucking scary. Sorry, that just reminded me when you said that. Good times. Okay. I think that kid was a spelling bee like national champion. Yeah. Okay, where were we? Okay, picture-wise. So we have this vector, this space curve like this, right? Let me draw a little small version of it. We still have our two vectors, or we have our vector r of t. So we still have it at point P, but as this vector gets closer and closer to r of t, because it's getting smaller, the 1 over h we said balances it out, so it still stays kind of long. And what we end up with is we end up with a tangent vector at that point. Okay? that tangent vector, assuming this limit will exist, gives me the derivative. So now instead of being the slope of the tangent line, it literally will just be the tangent vector to the curve. Okay?
Did we cover the last lesson?
Which one?
Did we cover the last lesson?
Did we cover this guy?
Yeah, not from first day, last first day.
No, that we're defining it today, what it is. Yeah, it hasn't, like, today is literally the first day we see this. But I want to show you some more examples. Okay, so hopefully this doesn't kick me out. Okay, so look, we're looking at that explore it thing again. So there's hella vectors here. Okay. So here is, oh wait, is it? Here's R of t on this curve right here, okay? The one that we were just looking at, not this curve, but just that picture that I was trying to draw there. Here is R of t plus h at different values of t, okay? At different values of t. And then here's that difference vector. Can you guys see that? It's a little small because it's on the curve. Maybe let me go like this. You guys can see it. Okay, there's the difference vector right there. And then here is the vector, the difference vector, but now being multiplied by the scalar 1 over h. And notice that as h gets smaller, that vector gets, oh, damn it, as it approaches 0, I'm getting this tangent vector right here. Okay, so that, notice it's approaching, can I go up? Can I zoom out? There we go. It's approaching the tangent vector as h gets smaller and smaller and smaller. That's kind of what's happening there. Okay? Applications of this, let me see if I can make this bigger. There we go. So this vector here, this is within Calc 1. This one will be called the secant vector. The vector connecting 2 points on the curve. And then the tangent vector is the one where it's just touching it at 1 point. Okay. So it says a space curve can be modeled by a path of a softball that is thrown by a pitcher. The secant vector of the curve show the average velocity between 2 points. And those points, as those points move closer, the secant vector approaches the tangent vector, which gives you the instantaneous velocity of the 2 points, depending at the points of time that the ball's at. So there is that, as Calc 1, there's the applications of secant representing average change or average velocity, and the tangent representing instantaneous velocity. Okay? These are some of the applications. This is why this topic is required for other science courses. Let me make some remarks. Similar to Calc 1, right now it's going to feel very Calc 1-ish. Okay, I'll just write down some of these things and then we'll take a break. All right, so first one is R prime of t. It's called the tangent vector at t of the curve. You see that? That's what that means. In this picture here. So I have my curve C, and let's say I want to find the parametric equations of the line tangent to that point. What were the ingredients to find the parametric equations of a line? point and not a normal vector, the direction vector that is what to the line? Parallel to the line. So if I want to find the equation of a tangent line, I'm going to use the point. How do I find the point if it's not given to me? And only the vector function is given to me? Well, I'm going to plug in, I'm going to use R to give me the point. Kind of like Calc 1, you use a function to give you the y value. Here we're going to use a vector function, R, to give you, the point. How do you find the direction vector of the line? It's parallel to the line. We're going to use the tangent vector. Okay? So the line passing through P parallel to R prime is the tangent line at P. And R prime will give you its direction. If C is a roller coaster and you're sitting down right here, R prime tells you the direction in which you're looking at. It says I'm sitting looking this way and the roller coaster is going in this direction. So the direction of R prime tells us the orientation of the curve. It's telling you which way you're moving through that. Oh, and its magnitude, tells us the speed that we travel. Tells us the speed. So it's very rich in information. This bad boy is going to tell you which way you're moving on the curve, and its magnitude tells you how fast at that point you're moving. If we want to ignore the speed or the magnitude, and we just care about the direction, we're going to normalize the vector. So we're going to take it's divided by its magnitude. But that has a name. So we define the unit tangent vector to be it's going to be special. In section 13.3 we're going to use it a lot. It's going to be capital T of t, which will be the derivative of r divided by the magnitude of the derivative. It's going to be a special vector, which we use a lot in this class. Okay, I got two more. All right, so thankfully, because this is a limit definition of a derivative, you guys learned a bunch of differentiation rules in Calc 1, right? So all those transfer to this, okay? Phew, okay. So using differentiation rules from Calc 1, we get that if R of t is parameterized by f of t, g of t, and h of t, Then, how do you think we're going to find the derivative of it? Yeah, we just take the derivative of all those. F prime, G prime, and H prime. And the reason that's going to happen, guys, is because when I take this limit, these two subtract. So then I'm going to have f of t plus h minus f of t over h. And then that limit is going to distribute into each of these functions because you're taking the limit of each of those. So each of these, you're taking the limit definition derivative, which is just the derivative of the functions. It's going to kind of pass on through. All right, last one. We say a vector function is continuous. If all its component functions are continuous. Which is what you guys covered in Calc 1. Okay, so we're going to use all that for the rest of the semester, okay? So let's take a break. I'm going to have you guys find the tangent line. Go over a couple properties and then we'll do some integrals. Okay? Well, let's take a break. So let's resume at 201. Resume at 201. Whoops, I left this. Sorry.
I'm pretty sure that's somewhere around 90 chapters. And somewhere there.
I'll have to ask him. I don't know if he's watched it yet.
I just want to really
Yeah. I'm enjoying it. I'm liking it.
How many episodes are there?
I think there's 8. Yeah, and they're each about an hour long. Yeah, it's juicy. I like it. Okay, guys. I'm gonna leave all these notes here. I have a practice problem that I would like you guys to try to work out. I kind of gave you some hints already. It's gonna feel very Calc 1. All right, so for the curve given by the vector function cosine t, sine t, and t, find the parametric equations of the tangent line at t equaling pi over 4. Yeah, pi over 4. Okay. Little picture here. We don't know what the curve looks like. Looks circular. It's got something like this. Looks something like that. What did R of t give you? Like, let's say here t is equal to pi over 4. Let's just pretend. Okay. What is that? What does R of t visually represent? The vector to the point of it, right? So what is that going to help you in terms of this point? That's the stuff I would like you guys to discuss with your classmates. Go.
I guess you can just find the tangent net of R2 and then just plot it.
Okay, yep, that helps with some of it. Yeah, keep on.
Oh, I have to find the point. Yeah, all good things that you're saying. Good. Work together with your classmates, put your minds together. You guys will do it. I believe in you.
We had a one-piece conversation.
We were just talking about the next show.
Oh, have you seen it?
Yeah.
Really, what episode do you want?
But I've never seen any.
Wait, are you?
But I'm hella listening.
That's all I care about. Yeah, my dad likes it too, and he never watches like any TV.
Oh, he's liking it too?
Oh yeah, he likes it because he's usually like a watcher. I never like does a show. So for him to do a show,
Sweet. Yeah, that is a big deal.
everybody just watches. I asked him. I basically was like working on the first day. We watched it at midnight, and then the next day we watched it
Yes.
Oh.
There's
a lot of people that like
Yeah.
which is so cool. Not a lot of people are like I know some people are like
They do. It's just
like other than
Really?
I don't
Let me know if you have questions. I'll walk around.
I think it's we just kind of do each part of it, right? Part of it, that's part of it, and the next part is
So the point of it is, yeah, everybody's
we just plug in the numbers.
So you
This here you have direction method.
because so like when you took the work I think that gives us like a general formula for
We have the
Yeah, can use like
I'm like, yeah, I know that's what I'm saying. One of those
Okay. Okay, guys, let's just quickly go over this. So if you want to find your point, what do you use to find your point? I'm just going to use R. So when you use R, you plug in a t value. Let's see what happens. So you plug in pi over 4. You're going to get, what's cosine of pi over 4? Root 2 over 2. Sine is root 2 over 2. The t is pi over 4. So you guys see these numbers here? That gives you the coordinates of the terminal point of that vector, which is why it gives you the point. Let me say that again, okay? Remember that this is a position vector that starts from the origin and it ends at the point that has those coordinates. So therefore, this tells you that your point P has coordinates root 2 over 2, root 2 over 2, and pi over 4. That's how R gives you that point. Now you're going to need your tangent vector, or actually we've been calling it the direction vector.
They're the same thing.
Which in this case are what you want. Yeah, they're going to be the same thing. The direction vector is the tangent vector in this case because you want the tangent. And so you're going to need R prime of t. Plug in 4, pi over 4. But you got to find the derivative first. Take the derivative. Derivative of cosine. Is that right? Yeah, right. Okay. Triple. Cosine t. And then the derivative of t is just 1. So then we plug in pi over 4 there. And then that should give you your tangent vector, which is negative root 2 over 2, root 2 over 2, and then 1. That's the tangent vector. That's the point. So how do you find the parametric equations? Review for the exam. To parameterize a line, you need your point, right? X naught, Y naught, Z naught. And then you need the components of your direction vector, A, B, and C. Right? So then it's going to be X naught, which is root 2 over 2, plus, or in this case minus, AT, so minus root 2 over 2t, Y naught, root 2 over 2, plus BT, root 2 over 2t, and then Z naught, which is pi over 4, plus CT, which is just t. Okay? And so yeah, so that line is going to be a line that's going to go, it's going to be right tangent to this bad boy right here, like this. You can confirm that on geometry. Anything you would like me to repeat? No.
Well, not a repeat, but why, once you have R prime, do you have to plug the pi over 4 back into it to get ABC? Why can't you just use negative sign?
Oh, because these are just functions. You want the actual tangent vector at that point. Yeah. Also, actually, this is a good thing to say. When you guys are finding equations of lines, parametric equations of lines, the results should be linear equations. I would have plugged, if I wouldn't have done this step and I would have thought this to be my A, I would have ended with root 2 over 2 minus, or plus, minus sine of t, and then that wouldn't have been a linear function. Okay. When you're parameterizing a line, all your equations need to be linear equations. If they're not, then you made a mistake. Okay. All right, so as you kind of saw with these remarks, a lot of the facts and properties that you covered in calculus kind of transfer over. Even all this stuff with the tangent and all that. So there are some properties I kind of want to go over real quick. I apologize for this part. I always hate writing properties because it's a lot of writing. Properties of differentiation. There's some cool ones though. There's some cool ones. Some are like, oh yeah, okay, I've seen these. And the others are like, oh shit, quite cool. I'm recording, right? Yeah, I'm recording. Okay, so let's start by letting V of t, W of t, and U of t be vector functions, and C a scale. Oh, hold on. Nope, comma. Yeah, this is where it's gonna start getting funky. F of t, a real valued function, like the ones that you saw in Calc 1, and C a scalar. Now we got three things we're dealing with. We got vector functions that input a scalar and output a vector, or input a number, output a vector. The old school type of functions that you guys learned in Calc 1, which input a number and output a number, and then just a number. Okay? So property 1 says, if I add up two vector functions, and I take the derivative, then, as you learned in Calc 1, I just take the derivative of each and then I add them up. Nothing too fancy. So take the derivative of a sum is the sum of the derivatives. Property 2 says if I have a vector function and I multiply it by some scalar c, what do you think happens? Take the c out in front and multiply it with v prime. Yeah, let me just write v prime. You take the c out and then just multiply by the derivative. Right, here's where it starts getting fun. What if instead of a scalar, I multiply it by a real valued function like this? Now what do you guys think about it? Kind of like this? Yeah. So it turns out it's no. Yeah, it's because see, this scalar is constant, right? It doesn't change with respect to t. But here, this will change. Sam. Product rule is what ends up happening, yeah. Because these are functions that end up multiplying. Here though, what kind of multiplication is this? Scalar multiplication. So it's a product rule in scalar multiplication version, okay? So we end up with f prime times the vector function plus f times the derivative of the vector function. What are the products that have we learned in this class? Cross product and dot product. So now if I want to do a dot product with another vector function, any guesses?
Yeah, prime.
It won't be zero, only if somehow this dot product, like, no, it won't be zero in this case.
Is that fine?
Oh, shit, I'm sorry. That's not a, yeah, that's just W. Well, these are like multiplying, right? So it turns out, remember when you take the dot product of two vectors, what do you really do? It's the sum of the product of them, right? So then you have, this has its own component functions and this has its own component functions, but then those component functions end up multiplying, like normal multiplication. And then that, when I take the derivative of it, is going to be the product rule. So what ends up happening through all that process, it ends up being a product rule, but with the dot product. Okay? So we end up with a dot product rule. Yeah. Like this. Which is kind of cool. All right, and then you guys also said cross product. Do you think that one also follows this? So that one's hella more complicated, right? Cross product. But because when you take the cross product, you again just end up multiplying like the components, you still get product rule to follow through. And surprisingly, it gives you a cross product rule. Which is, this one's definitely not obvious. Plus, if I write it down here, is it too, for folks in the back, would it be,
Maybe it's a zero.
you have, okay, you have it in there, okay. It's all good, it's all good. All right, what other rule did you guys learn in calc? Product rule, there was a chain rule, and there's quotient rule, but here we're not gonna divide by vector functions. We don't, that's not defined, okay, to divide by vector functions. So chain rule, yeah. But here I want you guys to guess, what do you think will be inside what? Let's say if I use V and I use F, what is defined? Which one can be inside which one? Yeah, can F, what things does V input? It inputs numbers, right? What things does F output? Numbers. So that's why it's okay for me to plug in F inside of V. But if I try to go the other way around, what does V output? What is this input? So I can't plug in V inside of F. That wouldn't be defined. Okay. So here you got to be careful, okay, with composition. So yes, so here it is defined to plug in a real value function inside a vector function. And yes, it turns out we get chain rule here. So it's the derivative of the inside function times the outside function, the derivative of the outside function with f of t inside of it. So it's chain rule. Yeah. Or like a weird chain rule. Okay. You guys were like at a upper division math class, your homework would be prove all these things. Okay? It's very tedious.
Analysis?
Stuff like that, real analysis, abstract algebra, those classes that you have to
Also
take.
like a new class that you're taking.
And the next class I'm teaching in the spring, yep, it's exactly the stuff we did. At the end of it. And so yeah, so you guys are gonna use these rules like you did in Calc 1, but now with vector functions. Oh, I thought that was my computer. Which one is that? Oh, is that? Okay. Yeah. Andres. Which one? This one? Oh, yeah, yeah, b prime of t. Thank you.
Don't throw some chalk.
I know. I won't throw chocolate.
I just want to.
Damn it.
Yeah, yeah. No, don't ever feel like I will do that. Yeah. It is, yeah. So these properties, sometimes they're practical to answer applied kind of questions, like this stuff, like where I'm using rules to give me information. But in other times, it's to prove things, which I'm not gonna have you guys do. But there will be some classes where we do proofs of things, and you'll see some of these show up. Okay. I'm trying to think of one. We're gonna see this one later on show up in a proof. We'll do that later. Okay. That will tell us something about the tangent vector and the vector of a function, and them being orthogonal. We'll do that later. But yeah, so these are not as like useful in terms of they're mainly useful for proofs. Yeah, they're mainly useful for proofs, but they also help derive other more complicated things. Okay, so this is differentiation. So now we're done with this part. Now we're going to go to your favorite part, which are integrals. Okay?
What's the theory?
Just students love integrals. I don't know what it is about integrals. I'm being super sarcastic.
So there is no quotient rule at all for,
There is no quotient rule because the only thing that makes sense to divide in this case would be something like this. But you can rewrite this like this.
But then what about our song?
Yeah. Low-D high, high-D low, that one. So then you can just turn it to scalar multiplication and then end up using this rule here. I mean, when you take the derivative of this, you might use calculus 1 quotient rule, right? But there's no like vector version for it because we can't divide vectors by themselves. Now, a cool question is, why can't I divide vectors? I'll let you guys think about that. Why doesn't it make sense to define that with these two that we discussed? That's a bonus. You guys can think about that. All right, guys. So let's do integration of vector functions. Okay, let me do a quick recap of integrals for just normal real value functions. I'm not going to go too hardcore into details. Recall the following for continuous real value functions. Real value functions. F of t. Here we're going to use t instead of x. Okay, let me remind you of what you guys did. So in Calc 1, you guys had f, and then you had f of t, and then you had your curve. And you had some curve for f, the graph of f. And then you had an interval from a to b. Okay, what did you guys do within that interval? You guys remember? With integration. It's been a minute. Area under the curve. Okay, you did find the area under the curve, correct. So you found the area under the curve. but you didn't do it with integrals to start with. You did something else with like little rectangular, yeah. You split up, you got your interval, you split it up into tiny little parts, all of equal size. My picture is not of all of equal size, but all of equal size. Okay, and then you made little rectangles with these. No problem. Make little rectangles, like that. And then what you did is you defined your integral from a to b. You said, okay, I'm going to get the height of each of these rectangles. I'm going to do that by picking, remember there was like the right end point, the left end point, the midpoint, all that stuff. And then maybe you covered that as these intervals got smaller, it didn't matter what t value you chose, because those rectangles end up just getting smaller. So then you call those t of I star. Some point in that little small subinterval. And then you plugged in that t into your function, and then that gave you the height of the rectangle. Okay? So to find the area, it was height times the base. You guys remember what you labeled to be the base? The change in t in this case, change of x, yeah, the change of t. And all these subintervals were the same delta t. They all had that same width. So this, you guys interpreted as the area of these smaller sub-rectangles. And then what did you do with all those areas? You took a big old sum of them, where you said, okay, I will be from 1 to n intervals. You split it up into n little subintervals. And then you did that, but you let n go infinity, so that you had an infinite number of subintervals. Okay, and so what you interpret this was the sum of outputs of f times lengths, which we're calling delta t. That's how you did this. You just took an infinite sum of that. And then is interpreted, I hope I spelled it right, as the area under the curve. Okay? That was a definition of a definite interval. And then you guys were like, I'm sure you hated doing this problem. Okay? But then thankfully, the fundamental theorem of calculus, part 2, came along and said, yo, I don't have to do all this. This is actually just equal to the antiderivative of the function that you're integrating, called capital F. Plug in the ending point, plug in the initial point, and that value is equal to this limit. It's kind of mind-blowing. Okay? And then for shorthand, you wrote this like this. Okay? So I needed to recap that because we're going to kind of use that type of definition to define what it means to integrate a vector function. Questions? Kind of look familiar-ish, kind of, okay. Okay, so for continuous vector functions, for continuous vector function r of t with component functions f of t, g of t, and h of t, we're gonna kind of copy this and define the definite integral, kind of the same way we did it for functions. We're gonna let the integral from a to b of rt dt let's copy the way we define that. We're going to just say it's the limit as n goes to infinity of some sum from I equals 1 to n, and then we have some interval, right, from a to b. Same thing, we're going to split that interval, but here it's confusing because it's not the x-axis or the t-axis. It's a t-axis, but it's not like corresponding to the graph. We're thinking of it as time, remember? So it's just some time from time A to time B. That interval of time, we're going to break it up into n little subparts and then plug in some ti's for each subinterval of time. And then multiply those by the scalar delta t. So I have a scalar multiplication here this time. It's a little star. It represents some time within a subinterval. Yeah. So usually you call those like Ti1, T1, T2, T3, and so on for the interval that you're picking. Okay. Okay, but this now it's going to be a little different. This is defined by these functions right here, right? So this is really the limit as n goes to infinity from 1 to n. But now let's write it in vector notation. Before I do that, hold on. You guys see how this is a scalar multiplication? A scalar times a vector, right? So what is this sum doing then? What kind of things is it adding? What's a scalar times a vector? What does that give you? A vector. So then what are we adding? We're just adding a bunch of vectors that are being scaled by delta t. Okay? That's what's happening. Okay. But let's see. So this is just f of ti star. Leave some space here, guys. Leave some space here. G of ti star. Leave some space. And then h of ti star. Leave some space. What do we do with the delta t then when you're multiplying it with a vector? What happens with a scalar when you multiply it with the vector? What do I do with that 10? It just multiplies to each of the components. So what do I do with this delta? I just multiply it with the components. And then I add all these up. I'm going to skip a few steps here, okay? Because otherwise we're going to be writing too much. But let me explain. I have this vector for t1. I have plus the same vector, but now for t2, plus t3, and so on. So I add all those vectors. What happens when I add all the all the first components? What will the final vector be? F of t1 delta t plus f of t2 delta t. Basically, all these just end up adding together. Same. Which one? This guy here? Oh, not yet. We're almost there. But basically, these are all individual vectors that are being added. So I'm going to distribute the sum into each of them because now I'm adding a bunch of things for each component. Right? Here, let me give you guys let me give you an example.
it's just educated.
Yeah, this just results into this. Right? So when I add a bunch of vectors, it's just the sum of the components now. So I distribute the sigma into each of these because I'm adding each of those now. Okay? Then I'm going to take the limit, and what we learned in 13.1 was that I can distribute a limit. Okay? So then what we end up with is we end up with the limit as n goes to infinity of I from 1 to n of f of ti delta t, and then I do the same thing with the other ones. And then I'm yeah. But now, you guys see this right here? Notice this right here is this. This is this. And the same thing for g of t, and the same thing for h of t. Right, this is just the definite integral of f of t. So then this just becomes the definite integral from a to b of f of t dt. Yeah. And then the definite integral from a to b of g of t dt. And then the definite integral for h of t dt. It's kind of fun. So to integrate a vector function, I distribute the integral and then just integrate each of its components. I could have just said that, but I think it's kind of powerful here to see all the stuff that's happening. And because of this, that uses fundamental theorem of calc, this is just this, right? It's the difference of the endpoints at the antiderivative. So that's kind of what I think Sam you were mentioning. Okay, so what ends up happening, we end up with the antiderivative of f subtracted at those values. Then you take the antiderivative of g subtracted at the endpoints, call that capital G. And then the antiderivative of little h, call that capital H. In this, you see how here we kind of invented this notation to really mean this? We're going to do now what we're going to do is we're going to say that it'll be f of t, g of t, h of t, evaluated at AB. Okay. Well, these are just the antiderivatives of little f, little g, and little h. So what does that mean? That to do one vector function integral, you have to do 3 integrals. Okay? I know. And this one might use trig sub, for example. This one might use a different technique. So I know.
So we can have integration table. I mean, take a test and we have to do integration.
Whatever fits in your index card. Yeah. Now I will say that I'm not going to give you an integral that's super gnarly because you've already been tested on that. I'm testing you on the stuff for this class that's applicable to this class. There might be a little bit of techniques, but I'm not going to have you do a 3-page integral. Fuck that.
The whole test one problem.
Exactly, I could just do that. Yeah.
No partial points.
Definitely partial credit. No, yeah, I wouldn't grade with partial credit. I'd be like, wrong, or right, if I did that. Ain't nobody got time. So I'm not gonna do something crazy like that.
So I'm just trying to
On the test.
visualize how you have the vector made of integrals would still be the area under the vector.
That's where I'm going now. Yeah, so yeah, great. Okay, so Dylan was kind of like, what is this, right? What is it? We saw the derivative was the tangent vector, so that kind of had an application. So now kind of like, what is this answer supposed to give you? Okay. What I want you guys to notice was, or what I want you to notice is that if I have the derivative in here, if I'm integrating the derivative, what's the antiderivative of r going to give you? Or what would it be? What's the antiderivative of this bad boy? Just r. Yeah, it'll just be r. So it'll be the vector function, but evaluated. And what does that mean? That means that each of the components will be evaluated. If this is the integral, sorry, the derivative. Check, yeah. Infinite decimal?
No, for the integral, you just read.
Oh, no. Be that kid.
Got the DT.
I forgot the DT. Smack my hand. Just kidding.
That was a test.
Yeah. Okay. Now, what is that exactly? Like, it's still kind of fuzzy. Like, what exactly that really means? Let me give you a physics example. Not too hardcore. So, a real world application. So let's let RT give you the position of an object on some curved path. Okay? Like what the stuff I've been showing you with like a baseball or something. Okay? Or maybe like there's a bird that's flying or something to some path. And this vector function like gives you the trajectory of it. So you plug in a t and it'll give you a vector, but then that point is where the bird's located at. So let's say that that's what this is supposed to do. Okay? If this gives you the position, what will the derivative give you? In Calc 1 for physics, if you've taken physics. It's going to give you the velocity of how fast and which direction the object's moving. Which I've kind of sprinkled a little bit, right? Like the velocity vector. Okay? So we have that the derivative gives the velocity vector of the object. We'll kind of dive a little bit more on this later on. Okay. Because remember that picture I showed you guys? The curve, some point, and then this was the tangent vector. Remember that? So this guy is going to tell you the direction in which the object's moving and the velocity of how it's the direction in terms of the velocity in the x direction, the y direction, and the z direction. Okay. Well, if we do what we just did here, and I integrate this velocity function from a to b dt, then that's going to be the position function evaluated at a and b, which is the position of the bird or the object at time b minus the position of the object at time a. What do we call that when you yeah. what you're gonna say, Jacob? Displacement, that gives you the displacement vector in this case. So here, the integral represents displacement. Okay. This gives us the displacement vector from time t equals a to t equals b. So you integrate, you do this infinite sums of all these different little velocities, and then the result ends up being that displacement. Okay. 2 problems for you guys. Here, this I'll erase because this will be not applicable. So we have 2 problems for you guys. Read the question. Read the instructions carefully. Okay. So let's let r of t, and this is going to be 2 dimensions. Let it be cosine t and sine t. So first thing I want you to do is I want you to graph r in R2. What does the graph of this curve look like in R2? Okay, graph it because you're going to use it. Graph it. Next, not too hard, but just find the derivative. And then I want you to integrate the derivative from 0 to pi over 2. Not too crazy, but kind of like, let's put everything we've been doing kind of together here. So graph it in R2, find the derivative, and then integrate that vector function. You'll see. Yeah. I guess I want you to, whatever answer you get here, try to interpret what it means from our discussion here. I know it's a little silly. Exercise set 3.
Yeah. Oh, you mean negative one? I got vector negative one.
No, the second one.
All I saw was the initial problem rushed into it. Oh, yeah, that's what I got though. There's, so I just turned all into one step, but vector 0, 1 minus 1, 0.
Oh, excuse me.
Yep.
For the first problem, do we have a prime there?
For the first one?
The first one.
No, it's just R.
The first one.
Oh, the third one. That's a prime. That's a prime. I did that on purpose. I know it's a little silly, but
So it's basically just R.
correct.
Yeah, that's very
Yeah. Okay.
But
Guys, this prime here is there on purpose, okay? I didn't make a mistake. I know it feels a little silly, but it's gonna make a point. Okay, cool.
Disconnected.
That makes sense.
How about the second one? You get negative sign.
You're gonna use.
yes, it's sin t because we get
You don't have to do the second.
Area under.
All right, guys, let's see. Hopefully, what did you guys get for number one? Circle of this is x, this is y. So circle of radius 1. Okay. Circle of radius 1, right? In polar coordinates. Circle of radius 1. Ooh, pretty good. Okay. So yes, how is it oriented? Counterclockwise. It goes in this direction. Like that. No, so think of t as theta. Right? So theta rotates in this direction. You do have to put the orientation because this is a curve that's parameterized. Yeah. Yes. If you think of the t's as just thetas, remember that theta rotates counterclockwise.
Is there a mathematical reason for that, or is it just by convention?
Oh, like y rotates in this direction and not the other direction. What does it rotate? Let me see. I think it might be that when t is between 0 and 90, so when the angle is between 0 and 90, you want both x and y to be positive. So you want it to be in the first quadrant so that it ties in with like all the stuff with triangles. I think that's one possible reason.
So it's mathematically by convention.
It's mathematically by convenience convention. Yeah. Okay, so this here, guys, help me out. What's the antiderivative of cosine?
Negatives.
Sorry, I'm stupid. Derivative. Sine of t, cosine of t. Yeah, thank you. Okay, and I know it's a little silly, I had you guys do that here. But when you integrate this here, sine of t, cosine of t, yes, it does give you r. But just to go off of the definition, that means I need to integrate each of these. This is how you're actually going to do it in the homework. And then you're going to have to integrate the other function. Right? You're going to distribute that integral. You integrate each one. So then you get, what did you guys get here? Cosine t from 0 to pi over 2 and minus sine, oh no, just sine, right? From 0 to pi over 2, which is, yeah, just this function from 0 to pi over 2. So then you should get -1, 1 as your answer. Okay? Now, why did I have to do this? Just so you guys we can tie it back to this. Okay? Let's pretend r is the position of an object. Where is it at time 0? It's right here, right? Time 0. Where is it at time pi over 2? It's right here. And we said that this is supposed to give you the displacement vector, which in this case was this vector. And that vector, how much do you move in the x direction? -1. How much do you go in the y direction? 1. So notice that's exactly this vector right here. Okay? So that's the displacement in this case. It's just nice to see it like with an actual concrete. So if you're integrating the velocity function from this time, it'll just tell you the displacement at that time. If you take the magnitude of it, it tells you the distance of that displacement. Okay? Yeah.
So instead of writing cosine evaluated from pi over 2 to 0 or sine t evaluated from pi over 2 to 0, can you just write vector cosine t sine
Yes.
t evaluated?
Totally. Yeah, you can just stick this part out here. Yeah.
So is this giving us the area under the curve for like negative sine t over cosine t? How does it relate to the integrated?
It has nothing to do with area under the curve. Yeah. When you guys in Calc 1, if you had a curve where this was the velocity, and you looked at A to B, that area represented the total distance that you displaced for the position of whatever this was the velocity. Yeah, so that's where it's kind of the same, but in this case, because the result is not a value, the magnitude doesn't represent area of anything in this case.
I guess my other question would be then, like, how does the integrated vector relate to the one that we're integrating? Like visually, is there any kind of comparison between the two?
Oh, between like the vector function that you get and the thing you're integrating?
Yeah.
The only relationship that besides algebraic, is that it's antiderivative.
Mhm.
But it's again back kind of to this. So this area that you get is the same value as if you were to, let's say this was f, right? And if I was to graph the antiderivative, whatever it wouldn't look like that. So let's say whatever it looks like, the difference in the y values, this difference is this area. Okay. So in this case, that's kind of how, it doesn't have area, but the difference of this, that's why I wanted to give you guys the displacement as a concrete example. In general, if this was the velocity of something else, it could be like, I don't know how that would look like, but, like, let's say your vector function give you the cost at one company, comma, the cost at a different company, comma, the cost of a different company. Then the derivative of that would tell you the rate of how that cost is changing for each company. And so then when you take the difference, it's kind of giving you the net change of that. So it relates to net change. Okay? In vectors though. Yeah. I think if you take the magnitude, that kind of helps out here in this case. But yeah, in terms of area, there is no area. That's what's uncomfortable. Okay, yeah.
Arbitrary question, but if the velocity is the first derivative, is the first integral of the position anything special?
Ooh, I don't know enough physics to know that. I don't know. Yeah, ask your physics teacher. I guess you can just say if for just a function, not even for a vector, right? Just say what's the antiderivative. Yeah, I'm not sure. What time is it? Okay. 10 minutes?
Yeah.
Okay, guys, I'm just gonna motivate 13.3. We'll continue it on Thursday. Oh, we won't. We have an exam. Actually, we have an exam. Hold on. I'm just gonna stop here. We'll stop here, okay? We'll continue 13.3. 13.3 is gonna be a doozy. So definitely let me put it to the side so you guys focus on your exam. So I'll stop here. Yeah, question?
The exam